Okay, this video is covering the second part of the fundamental theorem of calculus. So I would label this as section 4.4b. So before we dive into what the second fundamental theorem of calculus is, let's just do some exploration and talk about what it means to have a function defined as a definite integral. So if we look at this first statement, we have f of x is equal to the integral from a to x of h prime of t dt. What you probably noticed here that's a little confusing is that I've got two different types of variables. I've got the two x's and then I've got the two t's. The reason that is you have the function h prime of t, and we just have to introduce a new variable to eliminate confusion. And now f is a function of a different type of variable. So as x, think of this as the area, calculating the area under a curve. As we're accumulating area under the curve, let's say a is some constant, let's call it 0, and I'm calculating the area under this curve from 0 to 1. And we find that area and we write that number down. That would be f of 1. And f of 2 would be the integral, the area under the curve from 0 to 2, then from 0 to 3, 0 to 4. So we can create this whole new set of data and draw this graph of f based off of that data. So the x there is different from the variable for h. Okay, so don't get too bogged down by that. Just know that those have to be different variables, because then it gets really confusing. All right, so if I were to, what we're concerned with the second fundamental theorem of calculus is now taking the derivative of this function f that's defined as a definite integral. So we're going to apply what we know from the first fundamental theorem of calculus and kind of see what happens. So if I want to redefine f prime, or f, without the integral, we're going to apply the fundamental theorem, which says when I take the integral of h prime, then the answer is going to be whatever h is evaluated at my upper limit x minus h evaluated at my lower limit of a. Remember, a is a constant. So now if I calculate the derivative of that, h of x is a function of x, so that's going to be at h prime. H of a is a constant, so when I take the derivative of a constant, that's just 0. So you are simply left with f prime equaling h prime. Okay? But if you look at the second example, now your x is less than your constant. So let's see how that looks. So applying fundamental theorem, you get h a minus h of x. So h of a now is still 0 minus h prime of x. So this time, f prime is not simply equal to h prime, it's equal to the opposite of h prime because of that flip in where the x went. Alright, so then let's look at one more. The last one is going to be looking at from a to g of x, which think of g of x as a different function than just x. So it could be 2x, x squared, the sine of x, something like that. So if we do the same thing, we get h of g of x, which is our upper limit, minus h of a. So now when you take the derivative, you have this new function that's been introduced. So you're going to take h prime of g of x, but then times g prime of x applying the chain rule. Then, of course, minus 0. So make sure you are applying that chain rule if you have a limit of integration other than just x. And we really applied that up here as well, because if I multiply by, if I use the chain rule in these two examples, then you're really just multiplying by the derivative of x, which is just 1. So we're really doing the same thing. Okay, so now let's look at what the second fundamental theorem of calculus says, and it was basically what we just went over. If you're taking the derivative of an integral, and typically what you're going to see is these two different types of variables. You're going to see, you're taking the derivative with respect to x, and so that x is going to be one of your limits of integration, but then the other function is defined by t just to eliminate confusion. Okay, so the derivative with respect to x of an integral from a to x is going to be f of x minus, or f of x, yeah, times the derivative of x, which is 1. I'll kind of show the whole thing. Minus evaluate f at a minus the times the derivative of a, which is 0. And that's essentially what we just did. So this is going to go away, and this is just going to be f of x. Okay, so that one simply is, if I take the derivative of the integral, They just canceled each other out, leaving with f of x. But where that becomes different is when you have other functions there. So the derivative with respect to x from a to some function is going to be f of g of x, evaluate at the upper limit, times the derivative of the upper limit. Then minus the same with the bottom, but the bottom is a constant, so we know that's going to become 0, so this is the answer. All right, and for the final one, let's say we have two functions as our limits of integration, so that would be f evaluated at the upper limit times the derivative of the upper limit minus f evaluated at the lower limit times the derivative of the lower limit. So that really is like the main chain rule, or not chain rule, sorry, the second fundamental theorem of calculus is this piece right here. Okay? All right, so let's try some examples. Example 1. So we want to find the derivative of each function. And now you notice here that we now, instead of a lowercase f, we have a capital F. What capital F represents, just for notation, is capital F is the antiderivative of lowercase f. Okay, so that is equal to the integral of f. Just for notation, so when we use like f prime to represent the derivative of f, we use a capital F to represent the antiderivative of f. Okay, so typically when we see this, we think, okay, that's an antiderivative, and you can see that it is defined by an integral. All right, so we want to find the derivative of each function. So we want to find capital F prime, okay, of x. So applying our fundamental theorem of calculus, our second part of the fundamental theorem of calculus, all we have to do is evaluate this function, 1 over t, at our upper limit, times the derivative of our upper limit, which is 0, minus evaluate 1 over t at our lower limit, times the derivative of the lower limit. So when all is said and done, that is just simply negative 1 over x. And since it's a function and it's a definite integral, we do not need plus c. So I know we're left with a function in terms of x, but since it's a definite integral, there is no plus c here. Okay, so you can see that we actually didn't do any integration at all. Knowing how the second fundamental theorem of calculus works, you don't have to take any integral because you're taking the derivative. So what's happening is the derivative and the integral are canceling out, but you have to remember to multiply by the derivatives of the limits. Okay, so let's try example 2. So if I want g prime, so I evaluate at my upper limit times the derivative of my upper limit. But since my upper limit is a constant, we know that that's going to be 0. So we're going to have 0 minus, now evaluate at the lower limit, times the derivative of the lower limit. Now here's where people get confused because they then try to multiply by the derivative of the square root. No, the lower limit is x, we're multiplying by 1. So this answer is going to be the negative square root of x to the 5th plus 1. Okay? And then the final one. So now we have a different function other than x. So we have sine of x as our upper limit. So if we want to find h prime, we evaluate, and so every t that we see gets replaced with the sign. So we have sine x over sine squared x plus 1, but then you have to multiply by the derivative of sine, which is cosine. Then you subtract, same thing with the lower limit, but the lower limit's a constant, so that's just 0. So that's going to be sine x cosine x over sine squared plus 1. Okay? All right, let's talk about what this means graphically. So if I give you the graph of g, and then I say that f of x is equal to the integral from 0 to g. Now, based on what we've been doing, what we were just doing in our previous examples was taking the derivative of that function. So if I take the derivative of f, and I apply those same rules, then this is just going to equal g of x times 1 minus 0. So f prime is equal to g of x. So I'm going to go ahead and label that here so that I know my information. Pretty much every single type of question you see like this, you're going to be given the graph of g, and then you need to make sure and understand that that's equal to the graph of f prime. All right, so we want to find each function value and use it to plot the graph of f. So if I want to find f of 0, remember this is how f is defined. So if f of 0, this is my x value, and I'm going to plug that into the value for x here. So this is going to be the integral from 0 to 0 of g of t dt. And as we know of our properties of definite integrals, the integral from anything to itself is just going to be 0. Okay? Now f at 1 will be the integral from 0 to 1 of g. And again, I know that it seems confusing because you have a t here and you have an x here, but really it's the same thing, don't worry about it. Okay, so the integral from 0 to 1 would be the area under the curve from 0 to 1, which would be that trapezoid right there. So that's going to be an area of 1/2. Base 1 plus base 2, that would be 2 and 3, times the height of 1. So that's going to be 5/2. Okay? F of 2, F of 3, 4, 5, and 6. Go ahead, pause the video, calculate that for yourself, and remember that once you reach 3, you'll be subtracting area. So go ahead and finish that up, and then you can restart the video and see the answers. Okay, so I found each of those values. Hopefully you found them to be the same, so I would pause, check your work, make sure those are correct, and go back and change them if not. So now these are our values for the graph of f. So now on this blank graph, we're going to plot the graph of f. Go ahead and do so now. Okay, so there's our graph of f, which remember is representing the integral of g, basically. And if we connected this, we could kind of see that. And I also want you to see the exact curve of this, because where you have the lines, so from 0 to 3 is a line there, so that's representing kind of that parabola. And the line kind of changed a little bit direction, so it still looks like the same kind of parabola. And then from 4 to 6, you have a constant. So the antiderivative of that is just going to be like a straight line. It's not going to be a parabola anymore. So once we reach 4, it's going to be looking more like a straight line now. Kind of like a piecewise function. Okay, so now that you know some values about f, now you can make some, reach some conclusions about that graph. So looking at part B, you see at what value of x does f of x reach its absolute maximum value and its absolute minimum value. So looking at the graph of f, you can clearly see that the x value is, the absolute max is at x equals 3, and the absolute min is at x equals 6. So looking here at our values, you can see that the absolute max, the highest value was at 9/2, which is 4.5, and the lowest value was at -1/2. You can also tell by looking at the graph of g, which is f prime. Right here at 3 is where we had an absolute max, and so you can see that the graph of f prime changes from positive to negative with that occurrence, so therefore you would have a maximum there, at least a relative maximum. Okay, for this video, we're actually going to do one more example. The rest we're going to do in class. So the last example I want to do is example 4. Find the derivative of this function. So you can see now we have limits. Both of our limits are functions. So just going off of that same second fundamental theorem of calculus at the very beginning, this should not be too bad. So if I want to find the derivative, remember the derivative is canceling out with the integration, so that means that you don't have to integrate here. So just evaluate 1 over t at 2x, so 1 over 2x. Then multiply by the derivative of 2x, which is 2, minus evaluate 1 over t at x times the derivative of x. So then this is going to simply be 1 over x minus 1 over x, which just so happens to turn out to be 0. So sometimes you will get that. Sometimes you'll get the case where the variables do cancel out, and that's okay. But I just wanted to show you that example so you can see what happens when you have limit or functions in both limits. Okay, so the rest of the problems we will do in class and take any questions that you might